Hello everyone, it's me again. Once again, thank you so much for your time. Today, I'd like to continue on our discussion, which is the characteristics of component. For this video, I'm going to concentrate on wire. In fact, on the previous video, I actually done the part 1 series discussion on the characteristics of wire. Over that particular video, I have discussed the various parameters of wire that will affect the characteristics to determine whether they are suitable to use at a higher frequency. For this video, I'm going to use example, in fact, 2 examples, how to calculate and how to determine whether this wire with the diameter and also the length, whether they are suitable to be implemented as a short circuit at a higher frequency, such as radio frequency. Okay, so this is the objective of this video, is simply to use a simple calculation to determine whether this diameter and also the length of this wire, whether they are suitable to implement a short circuit at a high frequency. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by pressing the like and subscribe button. Please also turn on your notification bell in order to receive more information from this channel. Once again, sincere thanks for your strong support. As I shared with you earlier on, for this video, I'm going to have 2 examples. This will be the first example. The first example tasks us to find the resistance under the AC of a AWG number 22, okay, copper wire, okay, which means that the wire is made of copper at 10 megahertz, okay, using the data below. Okay, so this graph here shows the frequency versus the skin depth. Over this graph, you can see that 4 materials that are commonly used to make wire. Okay, for this question, basically using this copper. So I'm going to focus on this copper line as shown over here. So how can we approach this question? Okay, the question asks for 10 megahertz. So basically this 10 megahertz will move towards the copper line. And basically once it touches the copper line, I actually can determine the skin depth, okay, which is 0.021 millimeter. Okay, so this is basically the skin depth, okay, when the frequency is at 10 megahertz. So next, this is what I have done on the previous slide. Okay, basically the copper wire will have a skin depth of 0.021 millimeter. So next over here, okay, so this is a AWG22 cable. Okay, basically I know that the diameter, which is 0.644 millimeter. Again, how can I find this information? Okay, so this is the AWG table. Okay, so basically we are using this AWG22. Okay, from here I can see that the diameter, okay, you can see that this is diameter. I can see that the diameter, which is 0.644 millimeter. Can you see here? So therefore, I know that AWG22 has a diameter of 0.644 millimeter, which I have denoted at this diagram here. Okay, so this is a wire, and the equivalent circuit of the wire, in fact, can be a resistor in series with an inductor. Okay, so basically this is the equivalent circuit of a wire. At very low frequency, okay, the resistor basically is the same as the DC. Okay, when DC means simply a low frequency, okay, I actually can obtain that the resistor under the DC, which is 60.97 ohm per kilometer. Okay, again, how can I obtain this number? In fact, again, using the same AWG table here. So basically, over this column here, basically show the resistor, okay, per kilometer, ohms per kilometer. Okay, this particular column here. So basically, again, the question asks for AWG22. So therefore, I can obtain, which is 60.97 ohms per kilometer. Okay, so this is how I obtain this number here. Okay, the question tasks us to find the resistor under the AC. Okay, so this is our objective. How can we find the resistor under the AC? Basically by this equation. Okay, on the part 1 series discussion, I have discussed on this equation. Okay, so if you cannot recall, okay, so please take a look on the part 1 series discussion. Okay, but nevertheless, I'm going to discuss on this equation on the next slide. Okay, so this is the resistance, okay, under the DC. Okay, in fact, we also can obtain the area under the DC. Okay, how can we find this area under the DC? Okay, as I illustrate earlier on the part 1 series discussion, when the frequency is low, okay, the charges is evenly distributed on the whole cross-section view of the wire. Okay, so basically the current will basically flow throughout the whole cross-section view of the wire. So in order to find the area under the DC, is simply to find the shaded region of this conductor, okay, which is governed by this equation pi r squared. Okay, this pi r squared will let us to find the area of a circle. Okay, remember, okay, on this AWG 22, okay, we managed to obtain that the diameter, which is 0.644 millimeter. Okay, how can we get the radius? Is simply divided by 2. Okay, so from here, I can calculate that the area under the DC, which is 0.3257 millimeter squared. Okay, so basically, this is what we can done for the DC area. What happened here is basically when the frequency increase. Okay, remember on the part 1 series discussion, okay, I have mentioned this also. When frequency increase, okay, there will be a stronger magnetic field at the center of the conductor. When we actually have a stronger magnetic field, they actually become a higher impedance, okay, which discourage the flow of the charges at the center of the conductor. So therefore, the charges actually prefer to flow at the edge of the conductor. So this is what we call a skin depth. Okay, so I have discussed this on the part 1 series discussion. Okay, because at higher frequency, they actually generate a higher magnetic field. When the magnetic field is stronger, okay, basically they add more impedance to the charges, and therefore the charges do not like to flow at the center of the conductor. So therefore, they prefer to flow at the edge of the conductor. Okay, so how can we find the area under the AC? Okay, in fact, the area under the AC will be the shaded region. Okay, so if you still remember, how can we calculate this in the secondary school day? We learned that we can calculate the area under the big circle minus the area under the small circle. Okay, we actually calculate the area under the AC, which is also the shaded region, which is shown by this equation here. Okay, let's take a look over here. Okay, so from here to here is what we call a skin depth. And from here to here is R1. So how can we find R1 is also simply R2 minus the skin depth. Do you agree? R2 minus away the skin depth, I actually will be able to find R1. Okay, so this is how I can so-called rewrite the equation here. The R1 is simply R2 minus the skin depth. Okay, so how we can obtain all the R2, which I have illustrated earlier on, the skin depth, which I have done on the graph, which is 0.021 millimeter. So from here, I can compute that the area under the AC will be 0.0411 millimeter squared. Okay, so basically this is the area under the AC, and this will be the area under the DC. Under the DC, the charges is evenly distributed. Okay, so basically the whole area will be used to carry the charges. As for higher frequency, okay, they actually prefer to flow at the edge, and therefore the area under the AC is typically much smaller as compared to the area under the DC. So next, the objective is to find the resistance under the AC. Okay, so these are all the equations that I have introduced on the part 1 series discussion. Okay, so I can compute that the resistance under the AC. Okay, so this is the resistance under the DC, okay, which I have shown to you. In fact, is 60.97 ohms per kilometer. Okay, I'm not sure whether you still remember. It's over here from this AWG table. So under the DC is 60.97 ohms per kilometer. So therefore, this is how I obtain this 60.97 ohms per kilometer. Area under the DC and area under the AC, okay, basically I have showed to you over here. So I just put all the value here. Okay, I actually can calculate that the resistance under the AC will be 483.16 ohm per kilometer. Okay, so therefore, I can rewrite this resistor under the AC, which is 483.16 ohm per kilometer. Okay, so this is the first example which I done. I have compute the resistance under the AC. So next, I need to determine the inductor of a 1.25 centimeter length of AWG number 22 wire and its reactant at 10 megahertz and 900 megahertz. Okay, so I need to determine the inductor, when the wire having a length of 1.25 centimeter using this AWG 22 wire. I also need to know the reactant at 10 megahertz and also 900 megahertz. I need to determine whether this wire can be used as a short circuit connection at 10 megahertz and also at 900 megahertz. Okay, so this is what I need to calculate. Okay, I need to find the L value. Okay, so over here, this is what I have done earlier on. Okay, in order to use this equation, I need to convert all the unit to centimeter. So on the AWG table, basically they actually give us the diameter as 0.644 millimeter. Okay, so these are all in millimeter. So I need to convert them into centimeter. So this 0.644 millimeter, which is equals to 0.0644 centimeter. So I actually got the diameter of the wire of AWG number 22 as 0.0644 centimeter. Okay, so I'm ready to sub all this number into this equation. Okay, let's see how can we approach this question. I know the length of the wire, which is 1.25 centimeter. And I also know the diameter on the previous slide, which is 0.0644 centimeter. Okay, remember all the SI unit for this equation must be in centimeter. Okay, so I need to substitute all the length, all the diameter, all in centimeter. Okay, so basically this is 1.25 centimeter, which is shown over here. The diameter is 0.0644 centimeter, which is also substituted here. So from here, I can calculate that the inductor is actually equals to 0.011 microhenry. So I have calculated the inductor value, okay, which is 0.011 microhenry. So next, I need to calculate the reactance at 10 megahertz. Okay, so for a inductor, basically is governed by this radian L. Okay, so this radian is actually 2 pi f. Okay, for this frequency will be at 10 megahertz. Okay, the inductor value, which I have found earlier on here, okay, which is 0.011 microhenry. Okay, so basically from here, I can compute the reactant at 10 megahertz, which is 0.69 ohm. Okay, which I feel that is a very acceptable number because it's still a very decent small number. Okay, remember when we want to implement them as a short circuit, okay, we want this number to be as small as possible. Okay, so 0.69, I feel that is a really acceptable number to implement them as a short circuit at 10 megahertz. So next, I need to calculate the reactance at 900 megahertz. Okay, the thing is still exactly the same on the left-hand side. Basically, now the frequency changed to 900 meg. Basically, from here, I can compute that the reactance at 900 megahertz, which is 61.3 ohms. Wow, this number is pretty a large number. Okay, so therefore, I put a cannot. So basically, with this diameter and also with this length, okay, basically they are not possible to fulfill as a short circuit at 900 megahertz because it's quite significant as you can see from here. Okay, let's come to the equivalent circuit. Okay, basically at 10 megahertz. Okay, at 10 megahertz, earlier on I have calculated the resistor under the AC, okay, which is 483.16 ohm per kilometer. And I have also calculated the reactance at 10 megahertz, which is 0.69 ohm over here. Okay, so basically this is the equivalent circuit of a circuit at 10 megahertz. So next, okay, in terms of the equivalent circuit at 900 megahertz, okay, I have not really worked out on the resistor under the AC. Okay, but I think that you are definitely capable to calculate what is the resistor under the AC. Okay, so I leave this task for you to calculate. Okay, over here, the reactance at 900 megahertz, which is 61.3, okay, which I have explained earlier on, this is quite a significant number. So therefore, from here, I conclude that this diameter, okay, basically having a diameter of 0.0644 centimeter and also the length of 1.25 centimeter basically cannot implement as a short circuit when the frequency is at 900 megahertz. Okay, so from here, okay, I basically determine whether this wire can be fulfilled as a short circuit at a RF frequency. For example, at a 10 megahertz, okay, you can see that the number is still quite decent, okay, which is almost close to zero. So therefore, from here, I conclude that this wire with the diameter and also the length basically is possible to fulfill as a short circuit at 10 megahertz. However, when the frequency increased to 900 megahertz, okay, I conclude that okay, this number is too large to implement as a short circuit at 900 megahertz. With this, I'd like to stop my discussion. Please help to like and subscribe. Once again, sincere thanks for your strong support. See you guys soon. Thank you.